In this illustration, we'll analyze a situation where a man climbing on ladder supported by the counterweight. Here the figure shows a man of mass m holding a ladder attached to a counterweight of mass m by a string supported by a light smooth pulley. Here it is saying if the whole system is at rest initially, it is in equilibrium. That means the weight of man plus ladder is equal to that of counterweight. And man climbs up the ladder by a distance L1 relative to ladder. We are required to find the displacement of center of mass of the system. So here in solution we can write if M1 is mass of ladder, this implies we can write for the system to be in equilibrium, M plus M1 must be equals to capital M. This implies the ladder mass is capital M minus small m. Now, if we consider if ladder displaces by a distance L2 downward, as man is going up on ladder by a distance L1 and if ladder goes down by a distance L2, then here we use displacement delta y for man is equals to this L1 minus L2. Delta y for ladder we can write it L2. This is an upward direction, this downward. And delta y for counterweight we can consider as L2 in upward direction because it is attached to ladder only. So using these displacements of the three bodies here, we can find out the displacement of center of mass as delta y com is equals to, we can write for the counterweight as it is going up, we can use the relation as m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. So here we can substitute for m1 as counterweight, we write ml2. Then for mass of man, we can write m multiplied by L1 minus L2. Minus as ladder is going down, we can write m minus small m multiplied by L2 divided by the sum of these three masses, which is 2m. So on simplifying, we'll get delta y of center of mass is equals to, here m L2 gets cancelled out, a small m L2 can also be cancelled here. So we can write the result as m L1 by twice of capital M. That is the result of this problem.